Yes, it's time we can start. So, the last session of the day, we have two talks by graduate students from TIFR. The first talk is by Sagnik. He's going to tell us about the hardness of tribes function in the message passing model.
Thanks, Meena, for inviting me. So, this is a joint work with my advisor, architect, and so the title of the talk is "Tribes is Hard in the Message Passing Model." I will try to explain every word of the title consequently. Okay, so this is sort of break from the.
I think you're not audible at the back, so change the orientation.
All right, so I will just make myself louder than this thing. All right, so the idea is that this talk is on communication complexity, which is a sort of misfit, I guess, for today's theme. But let's see. We will start with a two-party model of computation, communication complexity model. So this is just a primer. Most of you already know this thing. This was first introduced by Andrew Yao back in 1979. And the model is as follows, that the idea is that there are two players. We call them Alice and Bob, as always. And they have inputs x and y. They want to compute a function which is a function of the total input, that is x and y. And usually this model of computation is used for proving lower bounds. So we can as well assume that they have unlimited power of computation, so that we can really focus on what is the communication that they need to do for this model. So that's the communication complexity two-party classical model. And we'll look at some of the functions which are like oft mentioned in the literature of communication complexity. One is called equality. Is evident. It's like the question is Alice has x, Bob has y, whether they're equal or not. It turns out that it's pretty easy if you allow Alice and Bob to have random coins. So this is randomized very easy. By the way, the whole thing, all these two-party models, there is a trivial upper bound of. So if x is of size n, x is an n-bit vector, y is an n-bit vector, there is a trivial upper bound of n, which is like Alice just sends a bit to Bob, and Bob computes the whole thing. So that is trivial. The question is that, is there any function which actually achieves that bound, meaning that you cannot do any better than the trivial one? So definitely equality is not such a one. And you can show that equality, you can do it by constant communication, like constant bits you communicate. Now here is another extreme, which is set disjointness, which means that you view this n-bit vector x as a characteristic vector of a set on the universe of size n. So now you can assume that Alice has a set, Bob has a set. They want to find out whether their set intersect. And it turns out that this is pretty hard, meaning that you cannot have any better protocol than a naive one. And there is a series of results. There is a Kalyani Sundaram and guy at 87. Then the proof was simplified by Razvorov, and there is a separate proof by Bari Yosef, Jairam Kumar, Shiv Kumar in 2004. In this talk, we'll be mainly interested in this proof, the last one. So,
what is the algorithm for equality? Like you'll get C by N if you have to send constant number of bits.
Yes, sorry, I didn't get it. So the algorithm for equality is that you do some sort of hashing. I will come to it in the next slide itself. All right. So we will just look at these two functions because these are two extreme functions. One is constant communication, one is linear communication. A little bit closely. So this is, let's say this is how I denote the input of Alice and Bob. These are the rows represent the n-bit vector that Alice and Bob get. So equality in the sense you are trying to say that if anything on the right side happens, this is equal, meaning that if Alice has a 1 at some coordinate, Bob better be having a 1 over there. And if Alice has a 0, Bob better be having a 0. On the other hand, if any mismatch happens, they are not equal. And so actually you are doing a bitwise XOR in each coordinate and doing an OR on the top of it. So this is equality, and I know and I just mentioned that it is pretty easy. thing is that the set disjointness is not much different from it. I mean, if you look at it, it's just the yes set is sort of lopsided, meaning that in the equality there was like 2 ways it can be equal and 2 ways it cannot be equal. In set disjointness there is 3 ways they can be disjoint and 1 way they cannot be disjoint, and that makes the complexity go very high. So the idea is that for equality there is an algorithm by hashing, meaning that you take the way this algorithm goes is that I'll give you Alice will like sample a random string from the public randomness, and she will do an inner product with her string, and will just send it to the Bob. And if you do it couple of times and Bob has the same string as Alice, then by looking at the inner product, Bob doing the same thing and looking at the inner product, Bob will make sure that, okay, I have the same string. This is sort of the hashing technique, and it can only work, it seems, that when you have this guys balanced, meaning 2, 2, not 3, 1. And whenever it's 3, 1, no hashing technique works. That's sort of the intuitive idea about why the disjointness shoots up. Now, this is the 2-party model. We will just extend this model to the k-party, there's a multi-party model. Now, there are different variations of multi-party communication model. One can imagine that one variation that we will consider over here is called message passing model, which means that suppose now we have many players. Instead of Alice and Bob, there are k players. And what they have is that they have dedicated channels within themselves, meaning that a pair of players have a dedicated channel. On contrast to that, there is a model which is called broadcast model. What is the contrast is that here if player 1 wants to send a message to a subset of players, she can afford to do it by just sending the message to those players by this dedicated channels. The broadcast model is different, is that whatever any player says, it is broadcasted, meaning that he comes and writes it in a blackboard and everybody can see it. So, I mean, both the models are very well studied. This talk we will talk about this message passing model only. So, what is this model? I mean, there's k player dedicated channels, but for proving lower bound, we will sort of distort this model and we'll look at it as this kind of model. By the way, this guy is called coordinator. Why this model is enough to look at the lower bounds is this follows, that we'll assume this coordinator is a guy who routes, meaning if player 1 sends a message to player 3, usually in the previous round he was sending the message directly. Now he will send the message to the coordinator and tell the coordinator, okay, send it to the player 3. And thus, just by telling the coordinator whom to send, you will get a log k hit because you have to mention which guy you have to send, and there are k guys, so it's a log k hit. But usually we are going to prove a lower bound of the full lower bound, meaning the trivial algorithm cannot be made any better. So this log k is okay for us. We can live with it. And this model has been studied extensively. So right at the 92, there was this paper by Dolev and Feder. They studied this model in a deterministic setting, both these papers. And there comes a randomized setting. And this is a sort of breakthrough paper which gave a lot of intuition about how to deal with message passing models. This is by Philip, Verwin, and Zhang. This is in 2012. And the technique they developed in this paper is called symmetrization. I will just give an overview what is the symmetrization technique. This is Woodruff and Zhang. They sort of refined this technique. So what is this technique? Very informally, the technique is as follows, that you actually try to view this k-party model as a 2-party model. Meaning that given a k-party model, you will consider Alice has one of the players. Alice will act as one of the players and Bob will act as the whole thing. And this defines a cut in the topology. And you will try to argue that on this cut, there will be a lot of communication. And you will also argue that by symmetrization, I meaning that this idea of symmetrization is this, that this cut can be an arbitrary cut. So take any cut, there will be a lot of communication on that cut. So totally there will be a lot of communication. Unfortunately, this thing does not work if you want to prove a lower bound for set disjointness. This is where the recent paper of Braverman et al. In the Stock 2013, what he mentioned is that this is not true. I mean, for disjointness, this might not be true even that for every cut there will be a lot of communication. But if you take all the cuts and sort of average over it, then there will be a lot of communication. All right. So that was the informal idea. And we are going to look through this work because our work is sort of heavily dependent on the setting they have developed. So this is where our work fits in. I haven't still explained what is tribes, but you will see that. So this is the lower bounds. By the way, all of these lower bounds are full. Whatever we are talking about today is full lower bound, meaning that we are trying to prove the naive algorithm is the best one. So this was done in 2004 by Yosef Jairam Kumar and Shiv Kumar. They showed that the two-party set disjointness that we have mentioned in the classical model is the lower bound is tight. The lower bound is omega n. That's the full lower bound. This was lifted for two-party tribes. I haven't mentioned what is tribes, but for the timing, it's a very closely related function to set disjointness. And they showed, by the subset of people, Jairam Kumar and Shiv Kumar, they showed that this is also pretty hard. Now there was a long pause after this, and 2013, this Braverman et al. Showed that if you consider k-party set disjointness in the coordinator model, not the coordinator model meaning the message passing model, this is also pretty hard. So the idea was that how to fill up this portion. Can we extend this idea and this idea to, or any other way to fill up this part of the square, and turns out that we can fill it up, which is our result that even for tribes function k-party communication coordinator model, it is pretty hard. So I will just now go into the main tools of it. Before that, I will just define what is set disjointness. I mean, for two-party set disjointness, you already know what it is. I just describe what happens if we extend the notion to the k-party model. So this is the input matrix. So here are the inputs. Each row now represents the input of a player. The set disjointness is true if there is an all ones column. This is sort of the negative notion. We are actually doing not set disjointness, because if you consider this vector to be the characteristic vector, by having an all ones column means that everybody has one element common, which is the other way of not set disjointness. But I mean, if you can solve not set disjointness, you can also solve set disjointness. So if you can find an all ones column in the input matrix, you give 1. Otherwise, you give 0. Now, why this is OR of ANDs? The idea is that you can put the columns as an AND gate and take an OR gate on the top of it, and the output would be exactly the set disjointness. Meaning that if there is an all ones column, there will be one AND which will be firing a 1, and that will just percolate out on the top. That is set disjointness. Now tribes is just that you take many copies of this set disjointness and do an AND on the top of it. That's all. Meaning that all these players are solving, let's say this arity is M, then all these players are solving M copies of set disjointness and saying that whether all of them are disjoint or not. And that's tribes. And so tribes can be written as an AND of OR of AND. So this is like one more level of set disjointness. And just to remind you, the number of players, we are dealing with k players. K can be anything greater than or equal to 2. This is the arity of the way you mentioned the bottom fanning. All right. So the main tool we used, and not we, like all the papers that the square we have mentioned, the 3 papers, all of them use some tool called information complexity. And what is information complexity? The idea is as follows, that information complexity is nothing but mutual information. So this is where the information theoretic technique comes in play in the communication world, is that you look at a player. Now in the coordinator model, what the player has an input. Let's call it x2. What is in this world, this literature, this communication between the players is termed as transcript. So we will use the word transcript from now on. So the player 2, what the transcript he is seeing is not the full transcript in message passing model. So he is seeing something called pi2, which is his own local transcript. Whatever the coordinator is feeding him and whatever he is feeding to the coordinator. The idea is that by seeing pi2 and by having x2, how much information can this player get about the other player's input? Well, this notion can be formalized by this following mutual information term. Meaning that if you have a player I who is having an input xi and having transcript pi I, how much information he is getting about other players' input. Alright? This is one way of looking at it. Now we can just look at from the viewpoint of the coordinator, which says that, well, coordinator can see all the transcripts. He knows what is going on, but what he lacks is the input. He doesn't have any input. So the idea is that by seeing all the transcript, how much he can deduce about the input of the players. This is can be sort of formalized by this notion that seeing the transcript, how much information he gets about the input. Now the information complexity is nothing but, information complexity of a protocol in message passing model is nothing but a combination of these two terms. It's meaning that by, when the protocol is going on, how much the players and the coordinators learning about each other. That's all. So this is the notion of information complexity we will use from now on. We will see later we have to fine grain it to work for our purpose. But it is not hard to see that actually this information complexity can lower bound communication complexity. Well, this is not for two-party. If we just consider this term, it's very easy to see that it's a mutual information, which is of course less than is equal to h of pi, the entropy of pi, and the entropy of pi is at most the communication size of the transcript, and the size of the transcript is at most the communication. That's like a simple thing. But when the some summation comes in, you have to come up with an expected argument, and that is not very hard to see. But anyway, we'll go ahead, and this is all right. So the trick of the trade is that whenever you come up with an information protocol, now you have the now you have the freedom to come up with a distribution over the inputs such that this mutual information terms gets as high as you want it to be. So of course there is this, these are random variables. This x is a random variable. Pi is a random variable which is a function of x. So if I take the main random variable which is x, you have to come up with a distribution such that mutual information terms are maximized. And you will try to maximize this as much as you can so that to prove a tighter lower bound on the communication. So the way it's done is that you see what are the protocols we can actually do, and how to come up with a hard distribution for these protocols. So I will just say the two Nike protocols which we can work on with. One is that coordinator probes. So just to remind you, we are talking on disjointness now, not tribes. And for the disjointness, I told you that the function will say 1 whenever there is a all ones column. So the protocol can go in each column and probe each player that do you have a 1, do you have a 0, do you have a 0, do you have a 0. And once he finds a 0, he just goes to the other coordinate and does the same. And whenever there is a column where there are all ones, protocol just coordinator says, okay, I'm done with it. Its answer is 1. That's a very simple protocol. The coordinator probes. You will see that this term, if I consider this protocol, this term cannot be more than n log k. Why? Because the amount of information you have to convey for specifying the first 0 of the column is log k. Because there are k columns, you have to convey log k amount of information, and there are n such columns. So it's n log k. This term cannot be more than n log k. But this term comes in rescue. This can push the lower bound, the information complexity to be as high as nk. So the idea is that for this protocol to work, for this protocol to have a hard time, you need to have less number of zeros. Why I'm saying this? Because whenever the coordinator probes, let's say if he finds a 0 on the next player itself, like within constant number of players, then even this term is not sufficing, because this term is then 2n or something like constant n. For this term to push up, you need to have 0. You need the coordinator to probe deeper, and that can be achieved by having less number of zeros in each columns. Now there is another protocol. It's just players send their input to the coordinator, as naive as it can be, and the coordinator just computes the disjointness. Well, this term is 0, because no player is knowing anything about the other player's input in this case. But the coordinator is learning a lot, and you will see that this term shoots up. So it's just a sort of trade-off that in these two protocols, one term is getting low while the other is saving. So even for these players to send their input, if you want this term to shoot up, there must be enough entropy in this term. So you need to have enough entropy. That's one of the requirements of the designing hard distribution. So how do you come up with a distribution which combines both? So let's look at them one by one. By the way, all these things have already been observed by Philip Verwin Zhang and Braverman et al. So let's look at the requirement and see how we can do it. So if you need to have less number of 0, I will go to an extreme. I will say each column has exactly 1 0. And you put the 0 uniformly at random location in a column, and fill everything else by 1. There's like as less number of 0 in a column as possible. And you need to have enough entropy. I will give it as much entropy as I can, is that I will put every bit to be 0, 1 uniformly at random, so that the entropy is as much as I can pack. Now you need both this distribution, both the properties of the distribution. So what you do a converse combination of these two distributions. Now this is sort of, we are approaching toward the hard distribution that we have to design. So we will, for the lessons, this is just a formal setting that we will introduce a random variable called m, which is a mode, which is sort of a Bernoulli random variable. Whenever m is 0, I will take the first distribution. Whenever m is 1, I will take the second distribution. Now this m is not exactly balanced, but that's for purely technical purpose. There's nothing to do with the intuition. Anyway, and for this hard distribution to work, we have to come up with a very fine-grained notion of information complexity. This is a pretty complicated term, but this is just a fine-graining of the term we have mentioned before. The one part is the player's information, and the other part is the coordinator's information. Do not worry about this term. It's just we need this way of saying it to make it work. All right. So now, what the idea is that I will just give you a very brief overview of how the proof of direct sum works. So how the proof of disjointness works, and we will see that how we extend it to the case of tribes. So I ideally like to prove something like this. Okay, so this is a typo. This should be greater than or equal to. Forget about it. So the idea is that given a disjointness instance, we like to say that the information complexity of the disjointness instance is n times the information complexity of and. Why do I want to say that? Because look at the structure of disjointness. It's an OR of ands, and there are n such ands. If I can say that for computing this disjointness, you have to compute all the ands, that's the sort of notion I want to convey by making this statement. After making this statement, only thing needs to done is to bound the communication of information complexity of AND. And if we can show a constant lower bound, then we are done, sort of. So how do I prove something like this? The idea is that, do I have 5 minutes? Or? Yeah. The idea is that you look at this distribution, you come up with something called a collapsing distribution, which means that you give zeros to this disjointness instances. I mean, meaning that this disjointness instance has to see all the ANDs to compute it. And this is not hard to see. This is not like very easy because Braverman has a paper on it. But yeah, that's the general idea of how to do with disjointness. For tribes, direct sum turns out to be not that easy. Well, tribes is one more level. So you can do the same direct sum argument for one level. Like you can say that tribes is at least m times the information complexity of each of these disjointness. But here is a problem, is that now we look at the disjointness instances. It turns out that these are one instances of disjointness. If I go back to the previous picture, you will see that this was a zero instance of disjointness. This disjointness was evaluating 0. Now we have one instance of disjointness. So there should be one AND which should evaluate to 1. How do we deal with it? So the idea is that, I mean, of course, I mean, this guy has to, all these inputs to this AND has to be 1. The idea is that, okay, fine, keep these ANDs to be the previous, take the inputs from the ANDs of this from the previous distribution and just embed all ones over here. So it turns out that works, but not for this information complexity measure. You have to sort of, yeah, this is like very technical. This is where Arkadav said I will lose everybody, but please bear with me. So this was the information measure we are working with, and we will just sort of like deviate it from it a bit. We will say that this minus W is saying that you do not care about that all ones. What about the other guys? How much is information? How much information is leaking from there? And sort of that you can work with this term. Of course, this better be a lower bound, otherwise the whole thing doesn't work at all. You can show that this works. This is an idea which is sort of we lifted from the JK's Jairam Kumar Shiv Kumar paper. So you can show something like this. Whatever needed, now what is needed to prove is that how do you prove a lower bound on this? Well, I don't have time to do this thing, but idea is that you can do it by some weird, refer to the paper if you want to know more about it. Alright, so the idea is that I will just say what is the main tool we have used in this idea. So the one main tool is the chain rule of mutual information. This is the normal chain rule of mutual information, which is saying that x1 to xn are random variables. You want to see the mutual information between them, you can write this chain rule. But the idea is that not only this, but you can also write for any permutation. Meaning that x1 to xn, you can permute them in any way and write the same thing. And this is like mainly used in our proof. And for lower bound disjointness, I will just skip it over because this tool has been used over and over again. This is something called Hellinger distance. Why we are using this? Because this Hellinger distance has this nice connection with mutual information. And Hellinger distance is a good approximation of statistical distance. So if you have a delta error protocol and if you put in two inputs x and y, you can actually bound the Hellinger distance between them, the output of the protocol. And this actually helps us to prove. Lower bound on disjointness too. So putting everything all together, I mean, we can prove this, and putting everything all together, this is how the chain of reasoning works. You first say that, okay, I want to prove a lower bound for the communication of tribes. You say, well, let's prove a lower bound on the information complexity of tribes. Now, how do you prove an information complexity lower bound? You say that, okay, I will prove an information complexity lower bound on disjointness and say that tribe is nothing but m times that. And then this is disjointness. For that, you have to go up to and In the Braverman's case, they went up to and, but we cannot actually go. We have to come up with a function called disjointness 2. What works is that this is also is lower bounded by omega k. So then we get the full lower bound. And that's how the whole proof works. I will just end here. Thanks. I'll take any questions after this.
Maybe the next speaker can start setting up. And
No, he has
meanwhile,
already set up.
huh?
Yeah.
Oh, it's the same laptop.
Yeah.
Okay. Is there a very quick question? Yeah. There's one question.
Sorry.
Yeah.
So subsequent to JKS, the other facts showed that you can actually do this for arbitrary depth.
Yeah.
So does the same?
I think it works. I think I have a proof, but I'm not sure. I have to talk to him. I have to convince him first.
Okay. So yeah, let's thank Sagnik again. And
Done.